This is lecture 3 for chapter 3 for ODE, and in this lecture I'll discuss Hamiltonian systems. If you start studying Hamiltonian systems or quantum physics, you'll see Hamiltonian systems that look a lot more complicated than what we're doing here. This is just the basis, but you have to start somewhere. Now, Hamiltonian system is a system, so we're using here a two-dimensional system that has some symmetry to the derivatives, and by this symmetry it allows us to calculate another function called the Hamiltonian, and there are a lot of principles that follow from that Hamiltonian that allow us to determine the solution curves of the system. Okay, what is the symmetry? And it's right here. There is some C1, that means some function with one continuous derivative, all first derivatives being continuous. Here's our system where dx by dt equals the derivative of this h. H is a Hamiltonian. Is derivative with respect to y. And dy by dt is the, and now this is important here, negative of the Hamiltonian with respect to x. Okay, the first thing you got to notice is there are many, as I said in the written lecture, many opportunities for mixing up the x and y's and making sign errors. For those of you who, like me, maybe rush around too quickly and maybe have a little dyslexia. So notice the y is here, but it's going with, the y is here, but it's going with the x. The x is here, but it's going with the y. And notice the negative sign out here. There's this classical story that was told in schools a long time ago, and the story was concerned sign errors. A lot of time we think, oh, it's just a sign error. But the story is the certain person, the professor, had someone in his family who bought a car and wanted to do all the maintenance themselves on it. So the person said, just tell me what to do, I'm going to change the oil. And they got into the car, and with directions they were supposed to turn that bolt in the pan a certain direction, and then the oil would come out and drain the oil out of the car. And as you know, when you're upside down and backwards and under the car and looking up and all that, things can get confusing, unless, I guess if you're a plumber, you know how to handle those sort of things. But this person didn't, and the person was turning and nothing was happening. Of course, the professor was saying, you want me to come into there and do it for you? No, I want to do it myself. So the person kept working very hard at this situation. After a while, the oil started coming out just a little bit at a time. You've probably heard the story a million times. And the situation was that the person had turned it in the wrong direction, had made a sign error, and in that sign error had turned the bolt into the pan, and so the oil was leaking out around the bolt that was now pushed up into the pan by great muscular effort of this person. So that's maybe you've heard that before, and if you haven't heard that before, I can remember when I heard it, and after I heard it I wasn't so glib about, oh, it's only a sign error. I know it's a silly story, but and it's not as big an error as a Hubble telescope disaster, but still, if it's your car, it is significant. So at any rate, what I'm trying to point out is there's sign error, there's opportunities for sign errors with these Hamiltonians. And if you start looking at the other systems in this book, which we're not going to consider, like the dissipative system and some of the others, gradient system, then you'll see things switched around yet one more time. So be very careful, that's all. So this is your Hamiltonian system. When the Hamiltonian system can be written so that the derivative with respect to x, the x derivative with respect to time is equal to the Hamiltonian with respect to y, and the y derivative is equal to the negative of the Hamiltonian with respect to x. And I said that the Hamiltonian was a C1 function, meaning it's continuous and all its first partial derivatives are continuous. So if the partial derivatives are all continuous, they can be taken in any order. That means if I have, well, I wrote it here, the second derivative of h with respect to x and y can be taken with y first and x second, or x first and y second. Hope I said those differently. All right, you can read it right there. Now go back to the original system. Let me try to show that. Okay, so here's dH by dy is dx by dt. Negative of dH by dx is dy by dt. So substitute those into this equation. So you can see what I did here. This was the derivative of y taken first, so I substituted dx by dt. And now I have the dx by dt taken first, so I substitute dy by dt. All right, now I've gone back to my original system. What I'm working towards here is a way to find out if the system is Hamiltonian. Now we'll write the system like we did previously. I will substitute here and here. So this becomes, okay, the partial of f with respect to x for a Hamiltonian system equals negative the partial of g with respect to y. Now if the system obeys that, so that these two derivatives are equal, then the system is Hamiltonian. So this becomes the test for the Hamiltonian, and it's based on the continuity of h and taking partial derivatives. And like I said, there's opportunity for inverting the variables, so you can be careful on that. This is f with respect to x, but remember this was the partial of h with respect to y. Okay, and here we're going to, this is negative the partial of h with respect to x, but we're taking this derivative with respect to y and this derivative with respect to x. All right, I've done enough lines on this page. And here it is typed out. When the system obeys this, satisfies this condition, then it is a Hamiltonian system. So that's the test that it's Hamiltonian. So here are some examples. One Hamiltonian system is the undamped harmonic oscillator. This is a classical Hamiltonian system, and we can write the undamped oscillator like this. Okay, so y is the function f, and minus q times x is the function g. Now if I take the partial derivatives, the partial of f with respect to x is 0. And if I take the negative of the partial of g with respect to y, it's also 0. They're equal, therefore it's Hamiltonian. Here's another nonlinear system that is Hamiltonian. It doesn't look like that harmonic oscillator at all. So here is the function f, and here's the function g. Okay, so I take the partial of f with respect to x. I'm sorry, here's f, and I get sine y. Now if I go in the other direction, I take the partial of cosine y with respect to y. I'll get negative sine y, but there's a negative sign here, so it ends up being sine y. They're equal, therefore this system is Hamiltonian. And now we'll look at one that is not Hamiltonian. Let's look at the damped harmonic oscillator. The damped harmonic oscillator has this extra term in it that we didn't have before. Here it is as a system. Again, this is f, this is g, and we take the partial of each one. We take the partial of f with respect to x, and we get 0. Okay, we take the negative of the partial of g with respect to y, and we get p. They're not equal, unless p is 0, in which case you have a non-damped harmonic oscillator. So this is not Hamiltonian. Now we'll look through some of the properties of the Hamiltonian, which is why we, whole systems are devoted to it. First, the Hamiltonian is constant along solution curves. So if you can find the level curves of the Hamiltonian function, those are also the solution curves. Again, I said previously that finding solution curves for a nonlinear system, it's very rare that you have a closed form solution or actually can plot them at all, have any kind of representation for them, but here in this case you do. So how can we show that this is true? All right, we have a Hamiltonian which we're just going to call h, and right now we're not specifying what its function it is. It's just some function of x and y, and we'll take its derivative with respect to time. Well, it's a function of x and y, so that's a partial of x, h with respect to x, dx by dt, plus a partial of h with respect to y times dy by dt. This is why you had to take Calculus 3 as a prerequisite for this class. Alright, now we're going to substitute from that system. Dx by dt, because it's Hamiltonian, is a partial of h with respect to y. And what about dy by dt? It's the negative of the partial of h with respect to x. So I substitute here and here, and remember that I have a negative sign, so my negative sign gets transferred over to here, and obviously that's 0 because it's h is a C1 function, so we can take these derivatives in any order. We're subtracting them from themselves, from each other, and we get 0. This shows that along the solution curves the Hamiltonian is 0. It's constant. The rate of change of the Hamiltonian is 0. Now, in the previous 2 lectures, we found nullines and looked at their intersection to find equilibrium points, or we tried to just observe them from the equations. But for Hamiltonian system, the critical points of the Hamiltonian are also the equilibrium points. So we have this functional form for the Hamiltonian, and we take its derivatives. We need to find the values x naught, y naught, where the partial with respect to y and the partial with respect to x are 0. Okay, these are the same points at which the system derivatives are also 0. And if the system derivatives are 0 at x naught, y naught, then x naught, y naught is an equilibrium point. And we had the Jacobian matrix, which we calculated and we used for investigating the behavior of the system near equilibrium points. So let's look at the Jacobian for a system that's Hamiltonian. Obviously, I did too much cut and paste here. This should be a y. Okay, so here's your Hamiltonian, but we know what f is. Okay, what is f? F is a partial of x, h with respect to y, and g is the negative of the partial of h with respect to x. Okay, so we're taking another derivative with respect to x. This becomes the mixed partials with a negative sign here. And here is the second derivative of h, partial derivative of h with respect to x, and here's with respect to y. Again, watch out for signs. All right, these terms on the diagonal, except for the negative sign, are the same. So the matrix is often rewritten using alpha, beta, and gamma, and I'll show you that on the next page, next slide. Okay, so this is how it's written. That mixed partial derivative is called alpha. So you see the alpha here and alpha here with the negative sign. Then up in the corner here, I could use different colors, couldn't I? This is a strange time to decide to be artistic. Okay, so here's that beta. Beta's right here. It's the second partial with respect to x. And now we have, let me see if I can find a better color or another color. Guess not. Okay. All right, we have gamma here. notice there's no negative sign, but there was a negative sign in that previous matrix. The negative sign is stored with the second partial with respect to y. So again, note the sign convention on gamma. Gamma is negative. All right, what is the trace of this matrix? It's 0, and the determinant is, you can work that out, minus alpha squared minus beta times gamma. So we can plug that into the quadratic formula. Here's a typical quadratic formula. Here's a quadratic formula here from chapter 2. The trace is 0, so this term is gone, and now we can work this out right here. Okay. So this gives us a nice form for that. If you wondered where that 2 went, okay, let's go ahead and put that through. Alright, the t is 0, and this determinant is multiplied by 4. The negative sign gets rid of these negative signs. The 4 comes out and gets canceled, and that's why there is no 2. So the eigenvalues are plus or minus the square root of alpha squared minus beta gamma, remembering, of course, what alpha, beta, and gamma are. And these are various partials of the Hamiltonian with a negative sign here. Now, you don't get all the eigenvalues and all the phase portraits that you did in other cases, in the general case for these systems. We have the case where alpha squared minus beta gamma is positive. That means the determinant or of the determinant of the square root sign in the quadratic formula is positive. In this case, the roots are distinct real numbers. Okay, so in this case, you're going to get a saddle. They're distinct real numbers, all right, but they're already fixed. Alpha, beta, and gamma are already fixed. There's not going to be a change in those, so you're going to get plus and minus, therefore you're going to get a saddle. If it's less than 0, you end up with a purely imaginary eigenvalue, and the equilibrium is a center in a linearized system. But in the general nonlinear system, it could be a center, or it could be a spiral source or a spiral sink. But for the Hamiltonian system, you have this Hamiltonian that's constant along them, therefore it truly is a center. Hamiltonian systems cannot have sources or sinks, or equivalently a spiral source or a spiral sink. So we see we can have a saddle, or we can have a center. Now you might have said we have all these great properties for Hamiltonian, but how do we find it? And that's, you're right, we have to find a functional form for the Hamiltonian. So we do that by integrating, and like this. Okay, if I have the Hamiltonian being a function of h and y, if I integrate its derivative with respect to y, then I will end up with a Hamiltonian, a form for the Hamiltonian up to some function that depends on x. So dh by dy is is f. So you integrate f with respect to y, and you get the Hamiltonian. You get a form here, and you'll get another function that depends on x. Obviously that would be part of the formulation. You could do the same thing by integrating g with respect to x, but we'll do it this way. Now, we know that the partial of h with respect to x is minus g. So this is the Hamiltonian. I'm going to take its partial with respect to x. So I'll have the partial with respect to x of this function f, or the integral of this function x, and a partial of this extra function phi. So I rearrange this, because I'm looking for phi now. I can do this integral, hopefully I can do this integral, but now I need to have a form for this phi of x. So the derivative of phi with respect to x is minus g, which is, okay, minus g is negative of dy by dt from this system, minus the partial of x of this integral of f. Alright, that's a lot of words. Let me erase this and I'll just kind of go over it again. Okay, to find the Hamiltonian, we start with that function f and we integrate it with respect to y. This gives us the Hamiltonian, but it's going to neglect the potential for another function, which is we call phi, which is a function of x only. To find an equation for phi that we can use to determine what phi is, we take another derivative of this whole thing with respect to x and we rearrange. So now we've used f here and we use g here. So it's not that bad. Let's look at an example. Here is a system where we have dx by dt equals y and dy by dt equals minus qx, which of course is our undamped harmonic oscillator. We determined previously that it was a Hamiltonian system. So the first step in finding the Hamiltonian is to integrate f with respect to y and know that we'll have an extra function phi of x that can't be determined yet. So when I integrate y with respect to dy, I get y squared over 2, and then I still have that function phi of x. Now I'm going to take the derivative and rearrange, so I'll have phi by dx equals minus g, which was minus this, so it's going to be qx minus the partial with respect to x of y squared over 2. Well, y squared over 2 doesn't have any x dependence, so that's all we have. The derivative of phi with respect to x equals qx, and we can integrate that. So to get phi, we integrate dphi by dx. Should have been dx in here. So that's minus g, which ends up being qx dx, and that is qx squared over 2 plus c. It's an arbitrary constant. We'll set it equal to 0. So now we have the Hamiltonian, which was the first thing we found, which was the y squared over 2. And then we had, remember, phi of x. Okay, now we know what phi of x is. So we have y squared over 2 plus qx squared over 2. And that's the Hamiltonian. So the idea is first you integrate with respect to y. Then you have another equation for that other function that's a function only of x that has to be added in. Usually you end up just integrating that with respect to x. It might be another term in there. Set any constant to 0 and add that back into your first result. So Hamiltonians have big physical significance, great physical significance, but it depends on the variables that you choose in your system whether you can see that significance or not. So we're going to have a harmonic oscillator, undamped harmonic oscillator, and we use a mechanical harmonic oscillator. So S is displacement and V is velocity. And here's the system. Rate of change of displacement is velocity, and the velocity is minus k over m times displacement. Okay, if I go through these steps like I did a few minutes ago, and you can just plug in from here, here's a Hamiltonian. V squared over 2 minus k over 2m times s squared. Well, that's a Hamiltonian, but it doesn't seem like it has any significance. Now watch what happens when I change variables. Okay, I'm going to use expression for momentum. Momentum is mass times velocity. So this is really the velocity, so it's 1 over m times the momentum. Then the other variable is going to be momentum, and that will be minus k times s. Right, because you already have the m right here. Okay, and you're looking for momentum. Now from this we construct a Hamiltonian, and it will have the physical significance that we expect, which is that the Hamiltonian is the total energy of the system. So I just went through to check that it was still a Hamiltonian system with these changed variables, and it is. We're going to put 0 equal from both sides, and so it's Hamiltonian. Okay, now when I plug in these variables from that what we did before to define that Hamiltonian, I end up with the Hamiltonian as a function of displacement and momentum is 1/2 mv squared, which is kinetic energy, 1/2 k times s squared, which is the potential energy. So if you have a Hamiltonian system and you expect that it will be the total energy, which is why you kind of motivates you to accept that it will be conserved in your system along your solution curves. If you don't get it looking like the total energy, perhaps you need to change a variable and then it will look like it. But no matter how you write the Hamiltonian, it will still be conserved along the solution curves. So we'll continue to analyze the system with the momentum and displacement as variables. So the critical values of the Hamiltonian are 0, 0, the origin. Here's the partial with respect to s of the Hamiltonian, and it's just a function of s, and the partial of the Hamiltonian with respect to p is only a function of p. Obviously the origin is the only point that makes both of these, at which both of these are 0. So the origin is the critical values, critical point for the Hamiltonian. It's also the equilibrium point for the system. Now we'll move on using the techniques of the previous lectures to find out how the system is behaving at this equilibrium point. So we're going to go back here and find that alpha, beta, and gamma. Alpha was the mixed partial derivative of h, which conveniently is 0, makes it easy. Beta, the second partial with respect to the first variable s, and it's k. Gamma, which is the second partial with respect to the second variable, which is p, and remember to make that negative, we end up with -1/m. We can plug into our little equation here for the eigenvalues, and we get a purely imaginary result. This is a center. Okay, the Hamiltonian is constant along solution curves. There should be a C. Okay, 0 will be one of those solution curves. Now if everything is a 1, for example, if mass is 1 and k is 1, which is why some math books like to do that, what do we have here? We have an equation for a circle. C would then be radius squared. Well, 2c would be the radius squared. I'll be radius squared over 2, sorry. If m and k are not 1, then the center will be nested ellipses. So let's give a little bit of a summary here. Of course, you can read the written lectures, and you can also look in the textbook or other textbooks on Hamiltonian systems. The idea of a Hamiltonian system is that the system has a certain symmetry, that there is a function h, which is called the Hamiltonian, and it's a function of x and y, and it's continuous with the continuous partial, with the first continuous derivatives. Actually, it's a C2 function, isn't it? Okay, now, should have said that, sorry. Okay, the structure of the Hamiltonian system is that the derivative of x with respect to t equals a Hamiltonian with respect to y. The derivative of y with respect to t is minus, negative, of the Hamiltonian with respect to x. And there's a certain test to see if the system is Hamiltonian, and here is the test. Right here is the test. This is f, this is g. If the partial of f with respect to x equals negative of partial g with respect to y, then the system is a Hamiltonian system. There's a method to construct the Hamiltonian, and here's the method. You take the function f and you integrate it with respect to y. This will give you the Hamiltonian up to a certain unknown function phi, which is only a function of x. By taking a derivative and rearranging, you can get an expression for the derivative of phi of x in terms of g, the other system, for the other system, minus the derivative of this integral. So to find phi, you integrate d phi by dx with respect to x, which means you're going to integrate this term, and if this is non-zero, you're going to integrate this term as well. You'll end up with some constant, arbitrary constant of integration. You can set that to 0. Add that in to this function, add that in here, you result in here, and that is your Hamiltonian. Sounds kind of cookbooky, but if you do it a couple times, you'll see it's, it is sort of cookbooky. Now, certain things we know about a Hamiltonian. First, we know that the Hamiltonian is constant along solution curves. So once you have that function, that form, you set that equal to a constant, and you plot the curves, the level curves of the Hamiltonian, you will have plotted the solution curves. If you want to find the equilibrium points of the solution, and we always want to do that, the equilibrium points of the system, then we find the critical points of the Hamiltonian. That is, we set those first derivatives to 0. We find the x and y values that result in those being 0. Typo didn't get any better. And those are also the equilibrium points of the system. Now we're going to want to study how those equilibrium points behave, so we want the Jacobian. But the Jacobian of the Hamiltonian is very simple. And here it is, using these mixed partial derivatives. But we abbreviate these. We abbreviate this as alpha. This becomes minus alpha. This we call beta, and this we call gamma. And because of the symmetry and the fact that the trace equals 0, we have a very easy expression for the eigenvalues. So here is that easy formulation for the eigenvalues. There's alpha, there's beta, and of course here's gamma. We also have a limited choice for the types of phase portraits. It's going to be a center, or it's going to be a saddle. The Hamiltonian system cannot have sources or sinks, okay, or spiral sources or spiral sinks. So in the next lecture, which is the final lecture for this chapter, I'm going to go over another Hamiltonian system, which is this simple undamped pendulum. This is another classic result of nonlinear systems that is covered in ODE. Again, these nonlinear systems are very interesting, and they warrant further study, quite a bit more study than we're able to give them in this class.